In this video, we're going to be talking about lenses. Lenses produce their images by refracting light. So in our previous video, we were talking about refraction of light. So refraction, we said it is the bending of the light waves as they pass from one optical medium to another. These optical media have different optical densities. Lenses are used to form images and to bend light. So we'll study the images formed by a thin converging lens in this video. Right, so the center of the lens is called the optical center. So that's this one. Then the symbol is C. The line through C, that is at right angles to the lens, is the principal axis. So that's the principal axis, this one. The principal focus is the point through which all rays parallel and close to the principal axis meet after the fraction from the lens. So this F there. So rays that are coming from the right will refract through this principal focus. The other name for principal focus is the focal point. So they're going to be refracted when they pass through the center of the lens, passing through the principal focus. Focal length, small letter f here, is the distance between the center of the lens and the principal focus. So from C to F, that distance there is a small letter f, which is the focal length. A lens can be thought of as a series of prisms, each of which bends the ray towards its base, as shown below. The center acts as a parallel-sided block. So they are. So remember, prisms. So refraction occurs differently. So the one that is coming through the center is just like coming along the normal, so it doesn't suffer any refraction. But then the ones coming either side of the principal axis will tend to be refracted. Now we want to find the focal length of a converging lens. How do you find the focal length of a converging lens? We use the fact that rays from a point on a very distant object, e.g. at infinity, are nearly parallel. So very distant point, our eye sees the parallel beam of light. So what do? We take a lens and then we move it on a meter rule until a sharp image is formed. So what do? You must have light that is coming from a window, from the side of the room, and then you see the image of the window on the screen wall there. So when the image is sharp, that's when you have found the focal length of that lens. So you then measure that. So the lens is moved on the meter rule until a sharp image of a window at the other side of the room is obtained on the screen. The screen could be anything that you take. Could be a whiteboard. Just take a piece of whiteboard and then put it there. That becomes your screen. So the distance between the lens and the screen is then roughly the focal length of the lens. Now we want to study images that are formed by a converging lens. First, find the focal length of the lens by the distant object method, the one that you've just done there. So after you've done that, you then mark on there. You now know the distance roughly of that's the focal length. So twice the focal length will be 2f. Then f from the center of the lens, then twice there will be 2f. So if you first of all perform this experiment to find the focal length, and then you have got to measure the focal lengths on there, and then you place your object according to where you want to find the position of the image. So the focal length f and f prime, 2f and 2f prime are marked either side of the lens on the meter rule. Illuminated object is placed at different distances from the lens, and the position of the screen is adjusted until a sharp image is formed on the screen. Now, the illuminated object placed at different distances from the lens, and the position of the screen is adjusted until a sharp image is formed on the screen. So if your object has been placed beyond 2f, that is here, beyond 2f, 2f is here, and then beyond 2f will be there, the type of image that you're going to form is going to be real. So by real, we mean that light rays actually reach the image, and it's going to be inverted, and it's going to be smaller than the object. So beyond 2f, you're going to form, let's just say maybe the object, image this side. So object beyond 2f, image will be between f and 2f. So it will be between f and 2f right there, and it will be inverted and smaller. Okay. At 2f, if object is at 2f, you form your image again at 2f, and it will be the same size as the image. And then between 2f and f, if your object is between 2f and f, then you have your image beyond 2f, and it will be larger this time. So as you can see, if you start with the object here, your image will be between f and 2f. Object comes there, the image is pushed further to 2f, but to be same size this time. Then between 2f and f, the object is pushed even further, that is beyond 2f, and then it's now larger. So it's the size is increasing as you are moving to the right. Now, as you move now, that is at f, you won't find the image there. It will be too large to be seen on the screen. So it is, we said, to be at infinity. And then if you further move the object so that it's between f and c, you won't find, there won't be any convergence this side. The image will be formed on the same side where the image is. So the image is formed on the same side as the object. And it is upright, it is virtual. In other words, no light rays actually reach the image. Image cannot be formed on a screen. So the image will be virtual and upright. When the illuminated object is between f and the lens, the image is virtual and is seen by removing the screen and looking through the lens at the light. So this is the application of the lens where you are using it as a magnifying glass. The image will be the same side as the object, and it is upright and it is virtual. We are going to verify this by looking at ray diagrams. So ray diagrams. So first of all, I'll go over this paragraph, and then I'll look at each and every one of these ray diagrams that are supported by the table that we've just covered. To find the position and nature of the image in a lens, ray diagrams can be drawn. For accuracy, the diagrams are drawn to scale on graph paper. The lens is represented by a straight line, and the object and image are represented by vertical arrows on the principal axis. Two of the following three rays are drawn. A ray from the top of the object. Let me use one of them as an example so that you can see on my cursor. So the first one is a ray that from the top of the object through the optical center. Top of the object through the optical center. Let's see. So we do have We do have our lens here. So you see this is our lens, right? If you take this one, again, this is our lens. We said a lens is going to be drawn as a vertical line with arrows, 2 arrows here and there. Now, suppose this is our object. So we are going to have a ray that is coming from the top of the object through the optical center, C, like that. So it's a diagonal line that is drawn like this. We're going to have a second ray drawn that is parallel to the principal axis, and then gets refracted through the principal focus, and it's going to meet the other ray that is coming from there, which is not refracted. It is passing through the optical center but unrefracted. So it's a straight line. Then it meets this one, which is refracted through the principal focus there. Where the two meet, where there's convergence, that's where our image is. So the image will be right there. The image is inverted. So it was like this facing up, now it's facing down. That's what you mean by inverted. Now, if you measure the image height, also the object height here, and then measure the image height there and compare, you will find that when the object has been placed between F and 2F, the image height is longer, like this. So you've got a longer image as compared to the object there. Now, there is another ray which has not been included here on the diagram, which is coming from the object, which goes through this principal focus straight until it gets refracted on there and goes horizontally until it meets the other two rays. So that's the third ray that you could draw as well, coming from this principal focus to there and then horizontally after getting refracted. So you could include that one as well. Now, magnification is the height of the image divided by the height of the object. So like I said, you measure the height of the object. So the image, measure the height of the object. So height of image over height of object will give you the magnification. You could also find the magnification by finding the distance of the image from the center of the lens. So distance of image from optical center over the distance of object from optical center. So that also tells you about magnification. And the symbol for magnification is small letter m. Now, the only way to do this one is to practice. So you need to really practice drawing these ray diagrams. Where I say the object, it is that then the object is beyond 2F, and you need to really draw that, and you do that on a graph paper, piece of graph paper, like I said. So if the object is beyond 2F, we draw our first ray that I talked about, straight and refracted. Second ray gets refracted at the lens, so at the center of the lens. And then through this principal focus where they meet, that's where the image is. Magnification would be that height divided by that height. Now, if you are asked to describe the nature of the image, you say that our image is inverted. It is real because there are rays that actually get to the image. And it is between F and 2F. So you can only establish this when you've drawn your diagram. You see that it is between F and 2F. So I suggest that you draw these rays so that you gain the experience of doing it. Applications for this kind of setup where the object is beyond 2F is the human eyeball lens and objective lens of a refracting telescope. Object at 2F is this one. Image will be at 2F, like we said, same size as the object. You can draw it to prove that it's the same size as the object. Applications, inverting lens of a field telescope. Then object between 2F and F, which is this one. The image will be beyond 2F. It is now larger than the object, as you can see. Applications, motion picture or slide projector, and objective lens in a compound microscope. So, and then object at F. Remember I said object at F, there is no convergence that produces the image. Remember, we need to have convergence to produce an image. So if there is no convergence, it means that the image is at infinity. And applications will be lens used in lighthouses and searchlights. Then lastly, we do have the object between F and C. Between F and C, then there's no convergence this side. Convergence will take place behind the object. And when you draw it in as a broken line. Remember, virtual rays, like in the mirror, in case of the mirror, I said you draw your lines broken, not solid lines. So these have to be broken lines that cause the convergence behind the object. As you can see, the image is not inverted, it is upright, and it is virtual, and it is magnified. In other words, it is enlarged. Then applications: magnifying glass or eyepiece lens of microscope, binoculars, and telescope. I think that is the end of lenses. So this topic is mostly done as practice. So you need to grab a piece of graph paper and do each of these rays so that you test your knowledge about them. Then you attempt these questions and let me know in the comments where you are struggling so that I can help. So you're going to do questions, maybe question 1 and 3. Question 1 and 3 only. Maybe you can do all. Question 1 to 3 is fine. And then you submit your work for marking. Signing out.